The good news, I actually did my homework. So I do have an idea how common, not easily to solve, min-max trees with repeated states are. The bad news, they're not easy. At least I couldn't find an easy solution. So, are we stuck with the abomination that was my algorithm from last time? Maybe. I did have some more thoughts though. First, maybe I just go for the brute force method of not having any cycles and just repeating the same tree over and over and over again, which is gonna make a massive tree, but it's at least gonna work. And then I had a thought, I can maybe simplify things, because if you look at the example tree I have here, does it actually? Okay, screen transfer works. If I have this loop, it means I just repeat the same nodes over and over, right? So I would expect down here just a copy of this entire tree, just branched off from here, for example. And if it's the same tree, it will have fundamentally the same results as this tree. So whatever I get as actual results from these nodes will be the result I get from the copied version of that. So if I just rely on the data I get from these, I can replicate things. The same I did last time, or attempted last time, only this time we're not gonna find a calculation for that. But we're gonna simplify things, potentially, this is an idea, by adding a counter in these nodes, so to speak. So we leave it at this graph, which includes cycles, but by adding a counter, we could sort of mimic having a full tree. That makes sense? So basically, if I want to traverse the tree and want to explore the different nodes, I have to go through this X amount of times. Like for these nodes up here, where there's no cycle, I would just go through once, and that's it. But for these, I could just increase the counter whenever I hit this while I create the tree. And I add the hard cap of every state can only be repeated X amount of times. And that's how I prevent any cycles in the long term. The problem that has, however, this whole setting a cap for how many times I can repeat a state doesn't really work reliably, because it's kind of weird. So if I don't want a certain state to repeat, it's very easy to do that if it's just 2 or 4 nodes in a row or states. So basically if both players make the same move just over and over and over again, then it makes sense to just abort the game at some point. I think that's how chess handles it, right? If it just constantly repeat the same states and no one actually changes anything else about the board, then yeah, okay. But if I go through, I don't know, 100 different steps before I reach the same node again, I don't think that should count to the repeated. At least that's kind of defeating the whole purpose, because then I have these 100 of steps that can repeat. It's a multiplier. Like if I say I can only repeat a certain state 5 times, it would be first mean that if it takes 100 steps to repeat a certain thing, that means still 500 states. Wait, what did I say? No, let's repeat 5 times and I have 100 states in between. Yeah, 500. Plus, I might repeat a specific state, but I might branch off in completely different directions every single time. So even though one specific state is hit more than 5 times, it is the only state that repeats and everything else is basically a completely different game. So a hard cap on repeating a node doesn't make sense. In that case, it feels wrong. So ideally, I would have this graph as it is. I would not simplify this down to a complete min-max tree or a semi-infinite min-max tree with a counter. And I would find some way to make that happen within the cycle already. So that's where my other idea came in. Had to drink something. That was not odd to tease out the tension. My problem is that I can't accurately calculate the score. Right? That's my issue right now. I cannot apply the normal scoring method, so I have no idea how to calculate the score. And without the score, the algorithm has no basis for making any decisions. So, what if we don't use a score? What if you use the basic idea of the min-max, just without using a score? Like, the way I would use the score is I make a tree and I evaluate it, set a score for each state, so whenever there's a decision to be made, I know exactly which of the decisions is better in that situation. I essentially calculate every possible game ahead of time, draw that out in a graph, and I just have to look up the numbers, which makes decisions during the game very easy. Because it's just comparison. I have 2 or more numbers, pick the smallest one, or highest one, depending on which player you are. Done. That doesn't really matter too much, because in the end decision is still just pick one of the different branches and then the number is irrelevant. You're not calculating anything with that number, you're just comparing the different numbers. So if I go here and one has, let's say 0.5, and this one is, okay, I'm still at the blue. So black. Say 0.5, 0.4, like that. I will compare them and pick this branch if I'm player 2, this branch if I'm player 1. So player 1 wants to get the higher number, player 2 is the same scores, just inverted. So minus, or 1 minus that score. So for player 1, 0.5 is higher than 0.4. Player 2 has basically 0.5 and 0.6. But yeah, that's all these numbers do. Just give a comparison. If during my calculation for all of this I don't calculate the score and just iterate the decision which side is better for one player or possibly all players, that would also help. Like if I have 2 or more possible decisions offered to me, I could just go with the one that is marked for this is player 1 branch, or the optimal player 1 branch. It does make a couple of things I usually would do with a min-max tree not possible. But I could do it. And I'm hoping, I haven't tried that yet, I'm hoping that maybe that solves the whole looping issue, but giving it a much easier go, like it's an easier problem maybe, and I can simplify things. So that's what I'm gonna try now. Again, that was just the thought I had this afternoon. Haven't actually tried if that helps in any way. Essentially, I would always break a node down into which decisions are good ones, which are the bad ones. The score would not mean this has a ratio of this many losses to this many wins. So the end nodes here would still be 1 or 0 in both cases. Just so let's say a 0 means this is a bad node, a 1 means this is a good node, which for these it makes sense. I lose, so it's a bad node. this one is a good node, I win, so it's a 1. Same with this one, it's a good node. Bad node. But then with the loop here, things get a bit more interesting, because what we did notice last time is I could tell that these 2 loops here, the outer one and the inner one, are different. We know they are different, so they needed different scores. My issue was that I could not properly tell which is better than the other with scoring, because I couldn't figure out an algorithm that gets the right scores. But if it's only a matter of which one is better, that I should be able to identify. So if we still... Actually, can I just... Yeah, let's just redo this loop again. So that was this full thing here. One over there, which... with that... full... empty... full... oh wait. Should move it to the side a bit. Do I? Ah, that works. Let's just... no, let's move it a bit. Is it there? It's better. And this one goes down to T. And it goes back up here. And this one has one empty going down there. Alright. And we had the entries, which was this one and another entry there. And then we had the exits. Which were all just a 0 and a 1, bad one, good one, bad one. So if we break it down in the loop, we still have the loop, okay, but we know how to identify those. Every node that has itself as an ancestor or a child is part of the loop, so we can identify those. And nodes can be part of connected loops or individual loops. We can have completely independent loops in the system. We have to treat them all on their own. We'd have to group them by having... yeah, okay, but that's doable. Let's not worry about efficiency. Let's just make some algorithm that does it. And now... yeah, this... okay, on this one on top here, this is where the decision has to be made. So we can ignore everything that doesn't have a decision to be made. So this one, there's only one way. It doesn't matter. Here's also just one way. It doesn't matter. No decision to be made. This one would have a decision. This one has a decision. This one has a decision. And this one has a decision. So this one is important. 2 options. This one has 2 options. This one has at least more than 1 option. This one is forced, and this one has more than 1 option. Did I forget one? No. So within the loop, so for standard min-max, we can just crap. Okay, that's pretty obvious way to find my problem. Since in a standard min-max, once I hit, even if there's no loop, just this decision alone here, guaranteed loss, down here would be guaranteed win if I have to split between the two. Normally I would have a score of 0.5. In this case, how do I evaluate this thing? Let's call it simplified min-max right now. I only compare different decisions. And the best way to decide that is by giving a score, like how many different endpoints will result in a win. Making the decision per branch is based on the score. Darn it. Oh, I thought I had something clever there. Okay, what if we use a hybrid system? Like, maybe use the standard min-max for the normal tree part, but then use the simplified one just in the loop for the important nodes, and then pick scores from the exits for the entry points based on their comparison. Does that make any sense? Could that work? I mean... Okay, what if we take the loop and then just pick out all the nodes with at least 2 children, so everything that offers a decision, and then just turn this into a table of how many combinations are there to go through this loop. How many unique combinations are there before we repeat? Wouldn't that means we make another tree for this looping part of our tree, this graph? And we basically reduce it to that thing. It's like dropping these other nodes that don't have anything to say. Okay, this is... I'm kind of desperate right now, but I'm also having fun. Honestly, this is... I haven't done stuff like this in ages. I already forgot how much fun it can be. I missed that. I really needed that. This kind of brain teaser. Okay. Which branch is better and why? So, for this one, which decision would be better? Okay, let's maybe make these simplified ones first. Yeah, decision is pretty easy. This one is better. This one has a win, so that's good. This one doesn't have a win. but we don't know how. Yeah, that all depends on what's... This has a 0 as a score, which is good. But if we take the normal min-max rules outside, this doesn't need to be a 0, just any score. For this one, I know I can get a win, but not necessarily. I can get a pretty good score though. Maybe I just ignore that there's a branch here and I just go, what's the best score I can get if I drop out here? And use that as the score for this. Which technically isn't quite true, because I can still go the loop around and get a better score up here, which is the weird part. Now if I do this in 2 stages, 2 passes then or more, then it just moved the issue further down the line. Which can be actually a good thing. Okay, but no. Alright, look. We can... If we follow this side, okay, if we follow this side, we get a score of 0. Or we can go further. So we have either a 0 or an unknown. For that one, we have either a 1 or an unknown. For this one, we have a 0. Wait, 0 was bad. That was not a good... Okay, I mixed the numbers up again. We have a 0 or an unknown. And for this one, now things get interesting because we have unknown or unknown. Alright, so the initial data that is accessible to us from just the standard algorithm, this is all the data we have. We're missing all these parts. But we can tell that these two are worse than this one. So if we rank them, then this one is on top, and these two we can't determine in order. You know, this node is better than these two. Makes sense. So if we take this node, we know we can hit this node again. So this is a repeating node, as is any other node. But this is also an entry node. Well, it's a decision-making node, so let's put it that way. This node has 2 options, which either lead to these two or to this one. And based on the data we have, we know this one will offer us better chances. We don't know the unknown score. We have to ignore them. We have to work without it. So if we just ignore them, since we can't determine them, we have either this or this. And if we pretend like those are the only options, like everything else is gone, then we can calculate a score with it. You can say one is a mixture of these scores, so a 0.5, and the other is a 0. Giving us a total of Now that's an interesting part. Do we treat that? No, we don't treat that as 3 entries with a third option. We don't treat that as 1/3. We treat it as 0.5 and 0. mix that up. So we have a 0.25. This one doesn't have any decisions. Wait, no, wrong. This one actually contains all of 3. Forgot, it goes around here, and then we'll hit this node definitely before going back. So yeah, we'll hit all 3. And we compare that to just hitting that one. Have I made a fundamental misjudgment in the last couple of times? Kind of. I always had in my mind that this side is worse than this one, at least for player 1. Because over here, you're pretty much forced to go down the road to this one where player 2 can win the game instantly. And here you have at least a chance to win. Player 2 can still go this way and prevent you from winning directly, but you could win. You have control over that up to here. Player 2 has control over that, so it's still in player 2's control whether you win or lose. But this is where you have a chance. But technically over here you also have a chance. But that just brings you back to the initial decision. Oh, I hate these cycles! I wonder if it's maybe best to just simulate that? Make a simulation of all the possible games and just increase the number of possible rounds and cycles and just see what the score will be like. And that way I get some kind of statistic that could maybe be used as a reference to make an actual algorithm. But that might be very specific to this exact graph. It might not be applicable to other graphs. Nah, not worth it. I might just get accidentally the wrong data and it looks a certain way, and then when I try a different graph, a different board, it makes no more sense at all. Going back to the loop. Oh no, but still, this set is technically better than this one, but up to here, there's no difference. These two should be equal, because in both cases, I make the decision. Though, no, actually, in this case, I have more chances to make mistakes than this one, so... Because I can go down this route. Over here, I'm forced to go down here. To that one. With this state, I have the option to make a mistake and go down here. So this is actually... No, this is worth after all. Which means this one is better than this one as well. So effectively, this node is worse than this node in terms of scoring, and then this one. So this one should be worse than... No, that still applies. Okay, this node is forced to go through all 3 exit states. These 3. This node can go all 3. So we have 2 that go through all 3. And 1 option here to go only through this one. Let's put it on that side. So if we put that in the score, they both... Okay, I was thinking if we take the score of all of 3 exits and apply that to both nodes, at least for the edges here, for where they can go. That's tricky. I feel like maybe I can have things cancel each other out, but that's only a feature here because they point to each other. What if we had the graph add another edge? What if we added another edge to the graph that goes from this node to this one? Like directly, and this edge didn't exist. They would both have decisions. Now, no decisions anymore. This one would only go through 1. This one goes through 3 before returning. Possibly returning. Actually, that's interesting. That means we still have 2 sort of connected loops. Wait, that's a kind of loop we didn't consider before. Was it just rephrasing? Wait a second, if I... Maybe one of my initial assumptions was wrong once again. Because why not? Why not make my life even more difficult? I'm never gonna finish this project, am I? But the point is not to getting it to an end state, it's just the journey that counts. I kinda needed this. Sometimes you need a project that will just humble you. Well, you're so great, can solve this, idiot. That kind of thing. So, this has interesting. Let's see, simplified. No, it's the same, actually. What's the term? Topologically the same? Kind of. It's still just 2 loops intersected where we have one loop and the other loop can... They both start at one point and intersect in another. Yeah. Okay, no, it's still just regular 2 loops, nothing special about that. It just looks different, but it's actually, if we reorder everything, it's still the same. Which is good, Let's just quickly get rid of that. And didn't get rid of that, let's try again. That's better. So going back to this. It has all exit points. This has the option for all exit points or just one of them. Does it matter that it has all exit points? I mean, we have to set a defined start somewhere, right? And then if we pick the entry node as the starting point, and consider all the different paths we could take to get back to this. That's something I should consider. I should not consider the different options I have for this node, but all the different paths I can take to get back to this node. So last time I was focusing on the exit points and looking how many ways do I have to reach them from each, but this time I'm focusing how many different paths can I actually take, which is a very different question. Like for this one, the answer is there's only one path. There's only one option. I go through here on the outside, go back. But from this one, I have 2. The bigger loop on the outside and then goes back, or the shorter one on the inside. And the thing is, if there's a third loop in here, which might split off, then that would add another path I could take. So right now it just happens to work out that I have 2 options to pick from in here, and also 2 paths I could take to go back. That's just coincidence, that's not a rule. So considering all the different paths I could take, this one has the options for 0, 1, or 0. This one has the options for 0, 1, 0, or just 0. There's more to consider here, because 0 or 1 has a different meaning depending on the color of the node I could reach it from. Like if this was the player 2 node, if it was their turn, this would be a lot worse than if it's my turn, because this would guarantee my loss. If I have control over that, that's good, I can avoid it. If it was player 2, I would have to assume they take the chance, it's out of my control. Same here, it's player 2's decision, and they're gonna avoid losing. If it was my turn, this would be better than what it is right now. So how do I get sensible scores outside? Doesn't need to be perfect scoring system. I don't need to have a clear... It doesn't need to be scoring... It wouldn't even need to be a perfect scoring system in normal max. Ignore what I said, as you should do most of the time. As long as I'm just moving around like this, which I consider this to be. Also, I notice I'm still stuck on this graph after 3 episodes. I've spent 4 hours on this now, maybe more. And I'm still on this graph and trying to tinker with it. I'm not making any progress, am I? Whoa! Why? Maybe I shouldn't stream at this hour. Maybe I should stream in the morning when I'm still fresh. But then I wouldn't have an excuse anymore. So let's keep it like this. Oh, maybe? Streaming on Sunday morning might be also quite interesting. Ah, thoughts for later. I could do the VOD editing and the... I'm getting distracted. I'm getting distracted. Entry points here, exit points... entry points here, exit points down here. Okay, all the different paths. Yeah, actually that's... Have I been doing min-max wrong the whole time? Okay, imagine... Okay, imagine a situation like this. This would be my loss. This would be win, this would be win. Right, this node, combination of the two, would be just 1. Which makes sense, just 1. This one is a combination of this and this node. So usually would just go for 0.5 and then move that up 0.5. But technically we should consider that this is the enemy's node. Do I actually need to make 2? Wait, did I remember min-max completely wrong the whole time? Is that an issue here? Well, I mean, I guess it would make things just more complicated in the end, so maybe it's best I ignored it. But yeah, this is not just a 0.5. If we assume the enemy, the opponent, I always go for enemy. I shouldn't do that. It's opponent. It's a friendly game of checkers. The opponent will always prefer the non-losing path. So if I have the option between this and this, okay, if we back up, this would be 1, this would be 0, this would also be 0, this would be 0.5, 0.5 with normal rules. So yeah, whatever. With the rules as I applied it so far, these two nodes would be equal. But they're not. Like, if I look at the game, it's... this side is definitely better. At least for me as player 1. On here, I have total control. I can just go over here. Player 2 doesn't have any choice. Has to go through this node. And here I have total control over... yeah, I want to use the winning strategy. Not the losing strategy. Yeah, what I've been doing wasn't min-max, was it? I've been using the average, which is an interesting way to do it, but that's not min-max. Was it? Right, so base scores, sure, but I should use the maximum and minimum. Should I? I mean, if I'm just going for the simple what's the best path to go. That's what I basically want to achieve here. But actually, no, that's not quite what I achieve. Yeah. The quote-unquote AI computer opponent I want to create actually needs these varied scores that just represent the ratio. But usually I would just go for this node is my turn. This is a 1 because guaranteed win. I mean, both sides are equal. Now we have two different values, but it's the opponent's choice, so this is basically 0 minimum. On this side I have this one is 0 again, two choices, but it's my turn, so it's a 1, so this is also 1, so yeah, going up I should clearly take this route. Okay, with that strategy I might not be able to do what I actually want to do, but maybe that's an easier way to handle it. So between these two I have an unknown and... okay, it's my turn. I have a 0 and an unknown. So this is an unknown. This is enemy's turn with a guaranteed win or an unknown. It's also an unknown. This is an enemy's turn with either guaranteed loss for me or an unknown. In that case, it's guaranteed loss. Like, I won't pick this choice, and the enemy opponent will not pick this choice, but the opponent will pick this one. Like, we want the minimum, right? You want the maximum, and that must be either this value or whatever this is. So it's gonna be at least this score, which is 0, which is not really much. And down here, it's gonna be the minimum, which is gonna be at most 1. Not helpful. And here, we're gonna pick the minimum as well, and the screenshot is stopped. Hooray! Please just reset yourself. Come on, focus. Here, just trying again. Yes, please connect. There we go, and we're back in business. Here we pick its opponent's 2 choice, so we pick the minimum. And that's either 0 or a value that could be higher than 0. So it's 0. So we know the determined value for this is going to be 0 with this system. For a perfect game, at least. So, congrats, I guess we have unknown, unknown, 0. Well, unknown, 0 or more, 1 or less, 0. So going on this side will guarantee us 0. Actually, since we defined that, can we... I mean, in this case we can maybe solve the loop, because now this is a definitive 0. Means this is a 0, which means this is a choice between 1 or 0. We take the minimum, which is 0, so this is a 0. That means this is a choice between 0 and 0, which means this is also 0. This is 0. And yeah, doesn't help us. Surprise, surprise. Because in the end, it just tells us that player 2 has a guaranteed win strategy and player 1 doesn't. And because it's everything just min or max, we don't have the proper way to distinguish between which side to pick, left or right. Even though I know that the left side is better because it offers more mistake opportunities. So that's also not the way to go. I don't like this at all. I'm thinking that maybe going through the blocked game after X amount of repeats, use a traditional tree, maybe simplified by adding a counter internally, so I don't have to actually store every single state multiple times for every loop. What I could do is kind of leave a trail. That could be interesting. So for the actual game, leave a trail through all the nodes. Oh, well, I guess for the calculation for the different games. I take a different path and I just storing a number in the child. That is the child's previous value, which starts at 0, plus my value, which initially for the root will be a 1. And then as I progress through the graph, it will just basically store a 1 everywhere and just mark it as, okay, I visited this node. No, I shouldn't add my number. I should just +1 it. I hit a node, I just make a +1 to mark my path down this road. So for straightforward, no looping, it's just gonna be once in all of these nodes. But if I make a loop somewhere and hit a node again, I add 1 to that node. And that way I would always be able to track how many times I've gone over a certain path. I could okay, if I do that, I'd keep the counter. Every time I visit a node again, I would increase the counter by 1. And I would also always remember the smallest number I've seen. No, that's... I didn't have a definitive start. Oh, I do have the start, that's not helping. I want to keep track of... Okay, what do I want to achieve? I want to see if I'm walking a path again. The exact same path I did already walk past. Just... Okay, this is getting into depth here, I guess. Not really. Traversing a path. Noticing that I'm repeating a specific segment exactly as I did before for the X amount of time. I can use the counter to track how many times I've seen a specific node. But I want to keep track of, did I repeat this specific segment exactly 3 times? Or did I go through this once, then went through here, then went through here again, and then through here, and then through here again? Because then this specific path was only 2 times. Even though I repeated this node, for example, 4 times. What if I increased the counter every time I hit a node? And once that counter hits the threshold on any node I visit, I'm checking if no. No, in-game that would be weird if I apply that to the actual game. What are the actual rules for repetition? Does the actual state count no matter how many times I repeat? Do I need to repeat the same state within a couple of moves? Or does it need to be just the same state at all a couple of times? Can you actually have an infinite game of checkers? Dang, I forgot the rules. There must be a rule system for that, right? There's one for chess, so there must be one for checkers as well. I mean, especially checkers. The late game, there's so much repetition possible. Even repetition on the long run, like you have dozens of moves you can do to not do anything. And if the opponent does the same, you will eventually end up in the same state as before. Also, I don't just want to... That could be an unfair advantage, or maybe a good one. Like if I just detect purely, it's exactly the same state. Doesn't matter how you reached it, or what path you took. If it's the exact same state, and you have had it a certain amount of times now, then the game just ends in a draw. That means you could force a draw in a disadvantageous position by forcing the opponent to repeat certain steps and you doing the same. Though that is clever gameplay as well, right? How would a min-max handle a draw? I didn't think about that. I always thought about definitive win or loss. Scores from 0 to 1. Just one number displaying the ratio between wins and losses. Binary. With a draw, I suddenly have this ternary system. I can't go at 0.5 because that's just not what the number represents. I could just attribute the draw to be automatically a win, since it's a win for both. Although it's also not one of the states I can represent. I would have a ratio between wins, losses, and draws. I guess I could just store that as a ratio itself. Just store all three values separately. I mean, in the end, my ratios are basically just... If we go for the normal standard... What the... Hello? Okay, that still works. Good, good. The standard tree, if I... Just don't like that. So this would be just 0, a 1, and a 1, 1, and a 0. Alright. Makes sense? This would be a 0. There's only one option. And this would be 1, 1, and 1, 0. 1, 1, 0. This would be 1, 0. Oh, this would be 1 and 1. And this would be a 0, 1 and 1. And this would be 0, 1, 1, 1, 0. Just, let's imagine I just use the counter, so... One column counts the losses, the other wins, and in my ternary system I have a third number. I mean, the original scores I needed were fractions, so basically just this turned on its side. Nah, sort of. The sum of this divided by the total number of possible endpoints makes more sense. I don't know, draw. Wait a second. Nope, nope, still doesn't do it. I mean, it kind of does. No, it does actually kind of solve the issue. Alright, this is gonna be weird. I'm talking to you about this now in the hope I find a mistake, because otherwise this would be too simple. I have my entry and my exit points. And I check all the possible paths for every entry point to return to that same node. So what I did down here, you know, for this entry point, for this node, the only path that exists will point me past every single of these 3 nodes, all the exit nodes. Well, this one has actually 2 options, 2 different paths it can take. One path will go on the outside and give me all 3 exit nodes, and the other path that's possible for one loop will only give me 1 exit node. Now we look in this, if we just try to count the sequence, and this is just how many wins and losses I have, not calculate the ratio, just calculate the pure absolute numbers. Like in here it was, I have 5 in total for the normal graph. I have 2 losses and 3 wins. So I don't calculate the ratio, I just calculate these 2 numbers. So I don't lose any information. And that means I have here, this would be, let's put out the gallop again. This would just give me 1, 0, and okay, this is, I need to 1, 0. The format of wins and losses, or losses, or zeros, ones. If I use that format, I have 1 loss over here and no wins, so this is 1, 0. This will be 1 win, 1 loss, no losses, 0, 1, and this will be another 1, 0. Pretty simple done is, but there could be any of these others too. So this would be a 2, 3, and this one would be a 1, 2 with this format. Whatever. Now with this system where I have take all the different paths I can take, it means this one has a total of 1 times all of these. So from this node I have only 1 times this, 1 times this, and 1 times this. So that means a total of 2 and 1. 1 plus 1 is 2, and only 1 over here, 2, 1. If I go with this one, all the different paths I could take are these 3 again, plus 1 time for these. So it's actually a 3, 1. And I can also apply the same logic to all the internal nodes here. Like for example this one would also be just... Actually no, to repeat this... Oh, this is interesting now, because I don't have the situation specifically with this node, because it's part of every loop, it's special in that way. This one was one of the non-special ones that don't appear on every possible path. Okay, let's assume a possible path includes I can only use every edge once. Once I've exhausted all the edges, that's not a valid path anymore. So every possible path from a node means every path I can take that will bring me back to that node while using every edge at most once. Maybe I should be stricter with the definition. But yeah, in that case, outer one, inner one, both valid path, and I would have 3-1, which is worse than a 2-1. I have 3 losses and 1 win, and here I only have 2 losses and 1 win. Like, clearly, the better ratio is this one. So this node is better than this one, which is what we want. And I can, when I'm inside this thing, make other decisions too. Like, okay, here I don't have a decision, so it's not really important. I might have other decisions, but I'm pretty sure I can still apply the rule of get through all the different paths. So let's see. Every path I can take here would go through here. Every path inside the loop, of course, would get me to here. So I have 1 times this, and would get back here. And that's it actually, because if I went to go down here and then back and then try to go down back up there, that would use this edge twice. So that's not a valid path, at least not according to what I need right now. So this node is pretty bad with only 1 0. This node here, I can go down this route, back up, or I can go down the outer route. So this node here is literally equal to this node up there. So it's a 3-1. Interesting would be now this node, because I can make a decision here. I have a 1-0 if I go out, which should be the worst option, because it's a guaranteed loss. This is a possible win, so this should be better. Let's see. Do I count my own node? I guess so. So path to take. Well, I can go through myself, down here, up there, down here, and back. Yeah, this in the middle, I can't take that. The only valid path I have with this. So I have a 2-1. Wait, no, that's not the node I'm interested in. To make a decision down here, I want to have the comparison between this and this. That's the node I need to check. Alright, for this I have this auto path, and that's it. So it's my own node, 0, 1, plus this one, 0, 1, 1, plus that one, 2, 1. So I have a 1, 2 versus a 2, 1. Yeah, and the ratio would be better for this side. One-third is better than 0. So it would, in this point, choose this option, which gives me a chance to have the opponent make a mistake. So that works. By simply not storing the score and just storing the ratio, I can actually calculate a useful value. All the way up. I don't have to work with any ratios as well, or any fractions, or decimals. I can always store everything as integer numbers, which means no rounding errors, if there are really weird cases where it's just one off. And technically I have an option now to include a third number for draws or special cases. I just need to change the evaluation then. If I just saw these sums, the different options, and my evaluation function needs to just compare these values, then I have implicitly a single strategic evaluation function that I can just change to handle draws as well. Like, how much more do I weigh in draws? Do I force the win, or am I fine with getting a draw as well? So for example, I could then, if I have 3 numbers and one representing the draws, if I say I don't want to lose, I could, for example, decide that I'm counting draws as wins and add them to the win ratio. Or I could consider no draws are not acceptable, in which case I add them to the loss, whatever. Or maybe make some part in between, like how overwhelmingly likely is it that I'm gonna lose? In that case, maybe try for the draw. Like, that could be interesting strategies suddenly available. This seems too easy. What's the catch? Let's see, I put that up here. Do I actually need to extract the loop now? Can I make this simpler by not extracting the loops separately and just... Let's see, in the endnotes, no problem. For the direct descendants, if everything is known for the children, no problem. Can I actually use the regular logic? If I go through here, so let's quickly delete those. Yeah, good. Made that on separate layer so I can clear all of that out. Right. So, using that logic still, this would be, I can make no more moves, that's a loss, that's a 0, 1. Oh wait, other way around, this is a 1, 0. 1 loss, 0 wins. 1, 0, this is a 0, 1. This then is also 0, 1. This is a 1, 0. And now let's look at this. If I don't evaluate the loops separately, which would save some processing time, which is good, I would now need to add to this 1, 0 the value I get from here. And every unique path I can take. If I now take this node and just go every unique path I can take from this node without repeating an edge, but just formulate it that way, I don't have to worry about loops anymore because that's implicitly solved because I can't visit an edge twice. Just go through here and would have, for example, further to the left, the 1, 0. Going down here, would hit the 1, 0, 1. Actually, can I simplify this? If I've already solved, for example, this one, I wouldn't need to calculate it again, so I can just use this value then. So left, 1, 0, take it. Then go this branch, go down, 0, 1, so I'm at a 1, 1. Then took that branch, then I can also take this route here, which has one option down here, just one from there, so I get a 2, 1, And I could go to the branch here and go back up. In which case I could go to the left to hit myself again. Which doesn't give me anything. Or I could go up here and go down there and hit this same node once more. No, I go down here. I could go over there and hit 0. Wait, let's keep track. First I had the left. This is gonna be extensive still. Alright, but it could work. Let's assume I always pick the left ref. Go to the left. 1, 0. Okay, 1, 0. Next option. Next chart. We're going always to the left. To here. 0, 1. Next option. That's all exhausted. For this one, I had more options. I could go up here. I'm forced to go down here. And now I have 3 options. That's another 0, 1. Or I could go down for 1, 0. Or I can go back up here, which has 2 options. One to the left, which brings me to myself. An endpoint doesn't count anymore, no score. Or I can go down this way. Wait, I went down here, or no, down here, and then up there, and this one also. Nope, it doesn't work. Because now I'm stuck at this point where I've already hit that edge, can't go further. That means I have suddenly a 2-2. Doesn't match my value from earlier. So I'm outside the loop now. Kind of disappointed. I was hoping this could go down a bit easier. It seemed so good. I mean, the loop version does work. But take the loop version after all. Maybe, okay, that's not the proper ratio, but it might still work out. Okay, let's just try to use it. Let's just pretend it is correct. Let's just see what happens if I use the score. Maybe it does work out on the end still for proper evaluation. It is not a 0.5 in my book for a regular system, but that doesn't matter for us right now. So that's a 2-2. Let's go for this one. We had the zero one from that. And the other option was here, going down to the left, 0, 1 again. Or going down there, 1, 0. Or going up here, going to the left. getting a 2-2. Are going down there. And then hitting stop. So this would now, in that order, be equivalent to 3-4. Which just... yeah, no, that doesn't make any sense anymore. Although... actually, again, it might work out. But the thing is, if I do this system... okay, look, generally... the ratio looks weird, because it means I have 3 losses and 4 wins, even though I'm definitely at a disadvantage. But in terms of just comparison between the different nodes, it's still good. Because yeah, this is actually a pretty good node. There's a chance that the opponent makes a critical mistake that will lead to my win. It's one of the only 2 places where that can happen. The other would be here. But I just realized with my system, as I use it now, the order of nodes makes a big difference. Because I calculated this first and that score was added to this score. If I did this first and then this one, it would be very different. Because it would just take that score and add 1 to the losses. So the order in which I handle the nodes is important. Okay, but this looks promising. The general values look weird in absolute terms, but relative to the other nodes, it makes sense. I feel like I'm so close. A solution without extracting the loops first. It does kind of make sense that if I start from this node without the loop back, I have a certain amount of possible end states. And with a loop back, that means that by going this route, I just add the values for this entire tree again. But adding them... no, wait, adding them to their current values. And by going down here, I can do that again. So a multiplication of the values I get from this thing, this node, plus a base value I have once from the other ones. Now by going different path in between, I can hit different targets. That's why I need to extract the loops. Now, this is not working out the way I wanted, but it's looking better. I'm in a really good mood right now. I can feel it. It's there. It's staring at me. It makes sense. I just don't know how to put it together yet. What do we do? What do we do? What do we do with the drum container? What do we do with the I should practice singing again. Completely forgot everything. And I get distracted once more. So the order matters. Can I figure out a way in which the order does not matter? Like for everything that's not involved in loop or branching, that's easy. Maybe I should... No, that's not reflecting the truth. That's not right. Promise with the multiplication I can change the values. And it can actually change the ratio. No, wait, okay, let's think about this. From this node, I can reach a couple of different endpoints. Let's start with that. Then by going back to that node, I suddenly gain access to all of that endpoints once more. So if I'm done at this node, I have access to this endpoint directly and this one indirectly. And I have access to all of these once more by just going back up. So that would mean initially I would have, from here, would have 1 access plus or 3, that's another 1 2 1. So x times 2, oh, let's write this out properly, 2x plus 1 and x plus 1. So by going back up, this is how the score would change. Every time I go to the loop, this is basically the formula I would get to calculate the possible end states, depending on repetition. And then let's say this one. It's going to be pretty much the same. But it's not just 2x, it's the number of states. My thought process is I have a fixed ratio directly available here, but the looping allows me to potentially change that ratio. Like if I start with a 2 1 and I add a 1 1, then I start with a 2 1, big advantage on the left, but then I'm at 3 2, 4 3, 5 4, and slowly but surely the ratio becomes more even over time. So it started with a clear advantage, but just repeating it suddenly goes to nearly 50-50. as we approach infinity, which is unrealistic, but let's just try to see the math. Or even more interesting, if we start with an extreme ratio, maybe let's go for 5, 1, and then just add 1, 2. Now first 5, 1, then 6, 3, then 7, 5, then 8, 7. In the end we have suddenly 9, 9, and then 10, 11. So by using the loop, the ratio flips. Initially, huge advantage, well, huge chance to lose, but because of the loop, we can slowly change the ratio to not even just even out, but to give us the advantage, and we can actually grow this further. Because on the long run, just adding these numbers up will mean that these two don't really matter anymore. So basically the ratio between these two numbers is ultimately what drives the whole thing. As we repeat and repeat and repeat again and again and again, this is the ratio we will approximate. There's a small difference from the initial absolute values we get, but it will tend to the one we get through the loop. Meaning that whatever we can reach from here directly without going back, all the paths that lead to end states that start from here, without repeating any edges, that ratio will be the prevalent ratio totally. Because it will overpower any ratio we could achieve with absolute values down here. But just repeating. But that also is now even question for whose player. Or whose player's turn is it? Because why would this player make the loop happen? This value is advantageous. Player 2 would not turn back up to the loop. So if I go up here and say the overall ratio for this node effectively is the ratio of this node up here, that doesn't make too much sense. Does it? Let's try something. Actually, let's go for 1, 0 here down again. That's fine. What if I start at the root? I still use the rule for unique path to every unique path that leads in an end state without passing over an edge twice. So every edge only happens once. We can have the same state, but we can't have the same edge. So I could take this route down here and then go to the left and down here. That's fine. But I can't go twice this path. I can have a specific state repeat however many times is possible without repeating the edge. So let's see, one path goes down here, and that means we have 1 0 1 0, and I'm just adding the numbers every step of the way. So on the left, then down here I make one right, go down here again, all left, 0 1 0 1 0 1. This is 1 1 now. Okay, this is gonna take a while. This is also 1 1. It's also 1 1. These are also all 1 1s now. Okay, left. Right. This time a right, so go down this one. Or left. Go left again. 0 1. This is now 0 2. Which might sound weird because this is only 0 1, but let's just play out the logic. This is 0 1. Because we just add the values from bottom. 0 1. 0 1. Then we go down here, and this is also now 0 2. And these are now all 1 2s. Going left. Maybe I should mark the path I already went through. Might be a bit difficult though. Yeah, so to say. So, yeah, went down left. Right. Down here, and I went down this route. Okay, then I also have the chance to go to the middle here, and going back that way, I'm at 0, so that's a 1 1. That's also 1 1. 1 1. This is now 1 2. This is a 2 2, and these are all 2 2s. Down here, left, and then lastly we go down that way. So we went down here, up there, up there, up there, up there. And then this choice left gets us nowhere because we don't reach an end state and just repeat something we already have, so we can ignore that one. This one also not getting us nowhere, so we can ignore that. Oh, that's not good. basically means we have to completely ignore this. It's as if this loop doesn't exist. That doesn't make sense. Oh, wait, no, it does make sense. It's not in this. If I'm starting on this left side, it doesn't happen, but if I'm starting on that side, I can actually repeat this loop. Got it. So it's still taking effect. Alright, so, but this path doesn't matter, so we are also through with that. And with that, we have all options on the left side done. Then right side, we can go down here, we can go left, down here, go on there. So that's now a 2-0. That's a 3-2. It's also 3-2. This is a 1-0. This is a 1-0, and this is a 3-2. The next option, we go down here. This time the right path, and then on the left, so 0-1. This is a 0-3 now. This is a 1-3. This is a 3-3. Wait, I think I made a mistake. So go down here. This was a 3-2. On. Okay. Why is it not showing? Yeah, it lost connection. There it is again. You can see it, yeah. So that's the 3-2, which just went that route. Then going down here next to the bottom, that's adding a 1 on the rights. So 0-3, 1-3, 3-3, 3-3. Then 1-1, 1-1, not 1-2. It's also 1-1, 1-1, 1-1, 3-3. Then going down here on the left side, we have the option to go there. We went down there, oh yeah. Then the right side here, then the left again. Another 0-1, so that's 0-4. That's a 1-2. I made a mistake earlier, didn't I? No, I didn't. That worked out. Okay, everything is fine. 1-2. Then this is also 1-2. This is a 1-4. And this is a 3-4. It's also a 3, 4. This is a 1, 2. That's a 1, 2. And that's a 3, 4. Okay, next path. Down here, go to the left, go to the right. Okay, so I went down here, left. All those branches went up there, went down here. Pick this one. So this is now a 2, 2. That's also 2, 2. That's a 2, 4. I hope I didn't make any mistakes right now. That would be really annoying. Because I feel like I should just try to implement this and see what happens. So 2, 2 and 2, 2. And that's a 4, 4. Okay, now we get something interesting. We go down here, go to the left, then go to the right. Go down here, head back to that one, and can only go downwards. But then we hit this node and can't reach an end state. So that's it for this side path. It means now we have the interesting option coming up. Okay, we're down here to take first the left path. 0, 1, so that's now 0, 5. That's a 2, 3. That's a 2, 3. That's a 0, 1. That's a 2, 3. That is a 2, 3, and that is a 4, 5. Whew. That's that path. Then this next path down here is a 1 in front, so we have 2, 3, oh, 3, 3. Oops, that's also a 3, 3. That's a 1, 1. That's a 3, 3, 3, 3. And the 5, 5. Finally, the loop happens. We go down here. And then make the decision to go back up, which leaves us the option to go to the right, to the left this time. Can't go down more anymore, but we can go to the left. And hit... Actually, which paths are optional? Can't go that route anymore, but we can go down here. Okay, first on the left, 1, 1, so that's now 3, 0. That's 5, 4. Five, 4. Then we go here, that's a 4, 3. Going back down, that's a 4, 3. Going back up, it's a 4, 3, 2, 1. Going back up, that's... Do I change this score twice? Let's update this score twice whenever I visit. So do it 5, 3, 4 potentially. And then up here that's a 4, 3, and that's a 6, 5. And then going down here again to the left. This time we go straight down. 1 0, that's 0 6. That's a 0 5. It's a 5 5. It's also 5 5. And going over here, that's 5 4. Go back down, that's a 4 3. 4 4. That's a 4 4. That's 2 2. Then that's 5 5. Or 5 4. Or 4 4. Depending on if I want to visit twice and then going back up, that's a 4 4. And finally we have a 6 6. Then once I'm done here, back up. Okay, go down here, go back up. I went to that side, went straight down. And now I can go this side. And I'm stuck because I already went this way. So that should be the final score, which is... looks bad. Assuming I didn't make a mistake, the initial decision is 2-2 versus 4-4, which is equal, which is not accurate. So again, in this case, it does not really matter. Ultimately, because both cases can lead me to there, but again, this side has the option for me to make a mistake. So it shouldn't be as good. Though I guess having more losses is bad. So maybe if the ratio is equal, pick the one with less losses. Let's see, what other decisions do we have? 5-5, 2-2. In this case I would pick this one, which has less losses, but this one is actually the better one, so that the same logic doesn't apply anymore. Over here I have a 3-0, 2-5, so yeah, that works out. Ratio is better for down here. What else do I have as player one? I have choices here, 5-5 versus 2-2. 2-2 versus 4-4. And 3-0 versus 2-5. That's all the decisions I have as player one. Player two has exactly the opposite goal. Can use the same scores. First decision coming up here. 6-0 versus 4-4. So yeah, picking this side makes sense. Down here, 0-6, not good. 1-0, good. 5-5. Okay, this one is better than this one, but this one is still better. Yeah, but these scores don't... Okay, maybe it makes more sense to just use 4-4 here. Just to indicate that is the path. And we don't update twice from the same path. That way the score stays consistent down here. Picking that side is the same as picking that directly. That makes more sense, I guess, in that case. Stays more consistent. But still, the rules are weird now. So that's bad. 2-5, clearly good decision there. This one is weird. I have left side is better than the right side. 2-2, 4-4. And then here, left side is better. 5-5, 2-2. So one time the smaller numbers are better, and the other the bigger numbers are better. It's clearly not. Unless there's something else I'm overlooking, this is not the way to go. And the loop strategy was better after all. Unless, of course, I am counting the loops. In the sense that I do explore the path uniquely, but then I do also allow the edges to be walked on twice, so I can repeat a path. More expensive in calculation, way more expensive, but that way I could actually figure out what the ratios are for repeated looping and see how that develops. Maybe then the scores look more correct. I should maybe make a model of this exact graph and let that calculate the different numbers. Might be easier. I think the method for just extracting the loops and calculating with this strategy in the loops could be worthwhile. Because that seems like I have an actual strategy now for calculating the values inside the loops, which I can then extract outside of the loops and use as normal, like over here. I think I'm gonna do that. Next time we're gonna try to make a model of this graph and just calculate some numbers, see if that does anything. And fallback is extract the loops and have the system mix the traditional system and the loop mechanism, combine the two. All right. See you next Sunday. Bye bye.